There was another problem with the Rutherford model. In addition to the hydrogen spectrum, Bohr needed to address the planetary orbits of the electrons. The electrons in the Rutherford model were kept in orbit by the Coulomb force between the electrons and the positively charged nucleus. But electrodynamics tells us that an accelerating charge emits electromagnetic radiation. And since the electrons are constantly accelerating, centripetal acceleration, the orbiting electrons have to lose energy. This loss of energy would cause the electrons to slow down. And in fact, this would occur causing them to spiral into the nucleus within 10 to the negative 11 seconds. Well, that doesn't happen. We're still all here. So let's look at how Bohr modeled the atom. We'll begin by looking at its physical structure. An electron is held in orbit by the Coulomb force. That force is given by K, or 1 over 4 pi epsilon, naught, times the charge on the nucleus Ze times the charge on the electron E, divided by the distance from the nucleus to the electron, R, all squared. Bohr made the following assumptions to address the shortcomings of the Rutherford model. It is called a semi-classical model since Bohr combined classical physics with emerging quantum theory. His assumptions are as follows. 1. Electrons can only revolve around the nucleus in certain circular orbits with fixed angular momentum and energy. The further away from the nucleus, the greater the angular momentum and the energy. Number 2. When in these orbits, electrons will not radiate electromagnetic energy. 3. Electromagnetic energy is emitted from or absorbed by the atom when electrons move between the orbits. The energy difference of the emitted or absorbed photons is the energy difference between the allowed orbits. Here's a diagram of the Bohr model. What we can see here are 3 orbits. We'll denote them n equals 1, 2, and 3. The higher the integer, the higher the energy of the orbit. What we'll note is that when an electron falls from a higher orbital to a lower orbital, for example here with this green arrow from n equals 2 to n equals 1, a photon is emitted, in this case with an energy E equals hf, where f is proportional to the energy difference between the two levels. Let's do a quick tour through Bohr's mathematics. You will be responsible for understanding and using the equations that end up being boxed as we go through. First of all, Bohr assumed that the angular momentum of each level is quantized and is expressed as follows. That L is equal, this is the angular momentum, which is equal to mv r sub n, is equal to n times Planck's constant divided by 2 pi, where n is an integer corresponding to the orbit. The Coulomb attractive force between the nucleus of charge Ze and the single electron of charge E that provides the centripetal force is given by F sub E equals the usual Coulomb force, Kze squared over r squared, is equal to m v squared over rn. So again, we're going to look at this part. Kze squared over rn squared is equal to the centripetal force m v squared over rn. When Bohr combined these two equations and did a little algebra, he solved for the radius of each quantum level and got that the radius, which is a function of z, the charge on the nucleus, and n, the energy level, was given by n squared h squared over 4 pi squared mkze squared. So by using classical equations for the kinetic energy and potential energy, angular momentum, Coulomb's law, Newton's second law, and Bohr's quantum assumption, the energy of the quantum levels in hydrogen-like atoms just fell out. It's E as a function of the charge on the nucleus, and the energy level is given by -1/8 times mz squared e fourth over epsilon naught squared n squared h squared. So here we have the mass of the electron, the charge on the nucleus squared, the electron charge squared, the permittivity of free space, the square of the energy level number, and of course Planck's constant squared. So now we're going to get to the key results of all this math. Using the radius equation from the previous slide, the Bohr radius a sub 0 is defined as the electron orbital radius for the ground state, that is, for n equals 1 of the hydrogen atom, where z equals 1. So a naught is equal to 5.29 times 10 to the negative 11 meters, or 0.529 angstroms. Radii of other hydrogen-like atoms are then expressed as follows: that the radius is a function of the charge on the nucleus and the energy level, and it's given by R equals n squared over z times a naught. So this is a key finding, and this is something we'll use again. Notice that the orbits grow in size as the square of n, so they get much larger as n increases, and they also diminish as z increases, pulling the electrons closer to the nucleus. By substituting all the values of all the constants in the energy equation given a couple of slides back, Bohr came up with a very simple result for the energy levels. The energy level is a function of the charge on the nucleus, and the energy level is equal to -13.6 electron volts times the square of the number of protons, or the positive charges in the nucleus, divided by n squared, the energy level of the atom. Notice how the energy levels are all negative, which indicates that the electrons are bound to the atom. The levels get closer together and closer to 0 as n increases. The levels, on the other hand, get larger as z increases.